Okay, so let's take a look at an example here. So here we're looking at the limit of x cubed over e to the x. So of course, as x goes to infinity, x cubed is going to infinity, and so is e to the x. So we have an infinity over infinity, so we take the derivative. Limit as x goes to infinity, derivative of x cubed is 3x squared. Derivative of e to the x is e to the x. So we still have an infinity over infinity. So we keep going. Limit as x goes to infinity. Derivative of 3x squared will be 6x over e to the x. And so we still have infinity over infinity, so we pull out L'Hopital's rule one more time. And finally, we're down to 6 over e to the x. 6 is going to go to 6. E to the x is going to go to infinity. Number divided by infinity. This thing is going to go to 0. And so one consequence of this example here is this can actually be expanded to any polynomial. Eventually, the derivative of the polynomial is going to come down to be a constant. All right, eventually. And of course, derivative of e to the x is always just going to be e to the x. So a limit like this will always eventually, of a polynomial over e to the x, will always go to 0. And what that means is, as a consequence here, is that e to the x actually outgrows every polynomial, no matter how big you make the exponent on the polynomial, is that e to the x will always outgrow it. It's growing faster, and we know it's growing faster because this limit is 0. And so that's a result we're going to have later on. But it outgrows it, it outperforms it. Okay, let's consider a second example here. Limit as x approaches infinity of the ln of x function divided by square root of x. Okay. Once again, this is an infinity over infinity limit. So we apply L'Hopital's rule, take the derivative. Limit as x goes to infinity. Derivative of ln is 1 over x. Derivative of square root of x, that's x to the 1/2. So that would be 1/2 x to the negative 1/2, or 1 over 2 square roots of x. Right. So this fraction can be cleaned up by saying, well, 1 over x over 1 over 2 square roots of x is the same as 1 over x times the reciprocal of this, which would actually get us to limit as x goes to infinity of 2 square roots of x over x. Okay, and then we can simplify that because square root of x is x to the 1/2. So using your properties of exponents, you have x to the 1/2 over x. That'd be 1/2 minus 1 would be x to the negative 1/2, which means this stuff needs to go to the bottom. And we have limit as x approaches infinity of 2 over square root of x. Now this is no longer an infinity over infinity limit. Okay, no longer a limit like that. So now I can just let x go to infinity. 2 over infinity will be 0. Okay. And so that was with just the little old square root of x. Now it turns out the process that I just did will always work with any positive power of x. So ln of x is outgrown by any positive power of x. And that's how slow the ln function grows. Is it grows slower than any power of x at all. Okay. So that's just kind of a little consequence there. E to the x outgrows every polynomial. Ln is outgrown by every positive power of x. You can like square of x, cube root of x, 10th root of x if you want, x to the 1/10. Right? As long as the power is positive, it will outgrow the ln function. We know that because ln divided by any power of x, that limit will always actually be 0. Okay, so those are a couple more examples of some infinity over infinity limits. And we're going to look at some other examples as well coming up soon.